You're going to leave recording the rest of the period.
Okay.
Or at least until I tell you otherwise.
It looks really cold.
This is cold, yes. This is cold.
Is it dry?
It is dry ice. Do you know what dry ice is, Cameron?
I don't know, that's the first.
I forgot the compound.
You forgot the compound? Okay, Brett, quiet please. So I'm going to put on gloves because it's a little bit easier to handle with gloves on. And I'm going to take out this chunk of dry ice today. You know what? This is hard to handle even gloves on. Because this glove has a hole in the finger and it was just burning me badly.
That's so cool.
What's the dry ice doing? Observe.
It's nothing.
It's letting off,
It's not mist.
Did you hear anything?
yes.
What did you hear?
Like vibration. You heard the gas.
I thought that was a
release.
phone.
You heard gas being released. You heard vibration. I heard those words. Very, very good. Both of them. That's why I didn't want you at the camera. Because that missing wheel every now and throws you for a loop, Philip. What other observations can you make, please?
It's weird.
You're hearing more noise. What do you think the noise is?
The gas is trying to
Yeah, it's
The
pushing.
gas is trying to escape
from under it.
from underneath it.
Yeah.
Okay? It's going that way. How come?
Because the table's tilted.
The table's not perfectly level, is it? It is like a puck. A really big puck. Yes.
Dry ice.
Let's do something and try and level the table a little bit. And so I have a old lab notebook over here, and Regis, if you could help.
Don't get in the video camera.
Yeah, we'll try and avoid that. Go down there and see if you can stick enough pages under it, not the whole book. Like open it a little bit, and we'll kind of play with that a little bit until we get it.
Film me.
Not. I can't see you.
Is that?
Let's see if that does it, because it was going that way, right?
No.
Still going that way a little bit. Give me a few more pages of paper. Maybe another 10 pages of paper, 20 pages of paper, something like that. Okay, we're getting close. We're getting really close. Okay, it's still going downhill just a little bit, and so I may try some other pieces of paper here in just a moment. What other observations can we make, please?
It's sliding around.
It's white. It's
White.
sliding.
Yeah, it's subliming.
It's subliming. What does that mean?
Turning from solid to a gas.
Turning from a solid to a gas. No one sees this melting into a liquid, right?
Correct.
Okay. Let's go back to what is carbon dioxide. What is it made of again? What's the compound? CO2. It's what we breathe out, right? We as animals, okay, when we respirate, we breathe in O2, breathe out CO2. So this is solid CO2. And they make it just by compressing it. They can push, 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 it gets really cold. And out of the air, CO2 comes into a liquid first, and it runs off. They make dry ice with it. Then oxygen drops into a liquid, and they send it off to hospitals. And then nitrogen drops into a liquid, and they send it off to welding supply stores and that kind of thing. And they just take normal air that we breathe, and they compress it, and they make these products. So this is dry ice. If we were to describe how much force there is between dry ice and the table, what kind of push or pull is there between the table and the dry ice to kind of open this up? What kind of push or pull is there between the dry ice and the table? What's going on? Because if I did this with a textbook, the same thing would not happen, right? Could you hand me that notebook next to you, please? Thanks. If I put this right here, it doesn't do the same thing. Right? There's a different kind of interaction going on. How come?
Because that's staying in one state.
Okay, we got about 5, 6 people calling out answers. Let's rotate. I heard you first, I think. Or was it Drew? Please go ahead. Okay, Regan?
It's staying. The notebook is staying in one state, and that's changing.
Okay, Cameron?
When the gas is being released from the ice, it's pushing against the table and pushing back against the ice and making the ice slide.
Okay. So, you said this is sitting still, doing nothing, and what was the word you used to describe this?
No, I said that was staying in one state, and that's changing.
Forgive me, I heard the word changing. Yes. Staying in one state, this is a changing state. And the way it's changing, I agree with Cameron, this is giving off gas, Can you see evidence of that?
Yes.
Right? We can see some kind of, almost like smoke, like a cloud coming off this thing. And that cloud, Cameron says, is pushing off the table. Okay? So it's able to slide really easily. All right? You got a hand up also, Brett?
It's like a hovercraft.
It's like a hovercraft. Okay? A craft that hovers. This is kind of hovering on the table, we might say. Okay? All very good observations so far. Now what I want to do with my hovercraft ice puck of physics right here is I want to observe if this sits perfectly still, and it was doing better over here, if this sits perfectly still and the table was very level, what would I expect would happen?
It would stay there.
It would stay right there, wouldn't it?
Yeah.
Okay? And so an object at rest stays at rest is one of these like statements you probably heard way back in middle school. Okay? And what I want to observe is I want to observe what happens if I give this a really brief push and see where it kind of fits into the world as we know it. So I give it a brief push, and let me do it over here. It's getting caught up on the frozen water and over there. I give it a brief push like that, and what does it do?
Keep going forward.
It keeps going forward. I heard there is no friction. What do you mean there is no friction?
Because it's kind of like a hovercraft. It's not pushing up against the table.
But it's still touching the table, so it's still.
Whoa, whoa, whoa. There's a lot of people talking and some are interrupting, and we don't want to interrupt. Okay? I want everyone who has the floor to have a chance to have the floor, and I want more people to begin speaking. So far I'm hearing a lot from about half a dozen people, and I'm really glad for those answers, but I do want everyone else to have a chance to speak as well. But go ahead, Drew. You said there is no friction. What do you mean by that?
Well, because of what he said that it's like a hovercraft. It's not really resting on the table.
Okay?
Do I make
I don't know if that's correct. But it's not because it's not on the table. There's no friction, I guess.
It's not on the table, so there is no friction, I guess. Okay, good. Cameron?
I made it different because the ice is actually on the table, but the vapors are making it slide.
Okay. The ice is actually on the table, but the vapors are making it slide, so you disagree.
Yes.
You think there is some friction.
Yes.
Okay. How could we test to figure out whether or not the actual thing's on the table or not? What could we do?
Slide the paper.
Piece of
Yeah.
paper on the table.
Yeah.
See if it'll slide over.
Okay, Zach, you have a piece of paper in front of you? Your homework?
It's not gonna get wet.
Okay. Let me see if I can slide this paper. Let me see if I can get it close enough to the table. Dry ice tends to float about 1/60th of an inch off the table. Okay. And so what I'm trying to do is get the paper so close that it can kind of scoot in and out. But it has to get within 1/60th of an inch because that's how close the dry ice is to the table. And that's actually pretty hard to do. What worked better, and I don't have it here, is they make something for working on automobiles that's a whole bunch of thin metal blades. And sometimes in a car, when you're spacing, I know when I was in high school, I used to have a 71, it's an old car, right? 1971, Volkswagen Beetle, old traditional thing. And you had to space the valves, and they had to be just a few thousandths of an inch apart, okay, the valves. And so you had a little thin metal blade you stuck in, and you closed them up until they were just that proper distance apart. I would need something like that probably to show this. The piece of paper was working a little bit, but not that well, because I think it's maybe just a little bit more than a 60th of an inch. And there's some air between the paper and the table, which makes it even a little higher. For right now, I want you to give me the benefit of the doubt. This is not touching the table. It was touching the table, Cameron, in the beginning when you heard it making the noise. Okay? When it was making a noise that was more like this, all that little vibrating sound you heard in the beginning, that was touching the table. But after a while, the bottom got very, very flat. And when the bottom got very, very flat, and it may do it again now just for a little bit. No, it didn't. Then it's no longer touching the table. It's actually riding on a cushion of air. Okay? So it's riding frictionless. How would we describe the motion of this? Please don't call out an answer. Just think about it for a moment. How would you describe the motion of this dry ice?
You want to know hands?
I didn't say no hands. I said don't answer.
I said no hands.
Caesar, what do you think? How would you describe his motion? sliding. Okay. Can you tell me anything about the way it's sliding? How it's sliding?
Sliding when you push it.
It's sliding when I push it? Okay, very good. It's a very good start. Edgar?
Like if you would just push it, it would keep going straight forward.
If you would keep pushing it, or if you pushed it, it would keep going straight forward. Okay? Amy, how would you add to that? How would you describe the motion of this block?
A really slow pace slide.
Okay? It's a really slow pace of sliding. It's not going very fast. Okay? I like that. Othman?
Floating.
Floating. Okay, good. Andrea? Is it Andrea? Sorry. I try and pronounce things correctly. I just forget once in a while. Andrea?
It's constant.
It's constant. What's constant?
The speed.
The speed. Okay. All right. Anything else? Brett, you got a hand up?
I was gonna say constant speed.
Constant speed. Okay.
And then
Andrea, what do you mean by constant speed? What do you mean by that?
When it slides, it stays like it slides at the same pace.
It slides at the same pace. Okay. How could we know if it was going at constant speed or not? How could we know?
Should have far distance.
Time trials. What'd you say, Cameron?
Slide it far distance.
Slide it for a distance. Okay? So we can make some measurements and find out if it's really going at a constant speed or not. Okay? What happens when the dry ice, this time I'm going to let it go. I'm going to push it, I'm going to let it go from one of the tables to the next. Because so far I've been sticking to one table with my experiment. What happened?
It caught an
the
edge.
tables aren't even, so.
Oh, the tables are not perfectly even, so it must have caught an edge, I heard.
I don't really think it's that. I think it's like since you've been sliding
Yeah?
dry ice on one table, like you got used to it, and then when you switch it to another table, like it's not used to like I guess
But it's the same surface.
Okay.
surface.
Let's see. I'm going to try and make a crossover here. It feels a little more smooth over there, the two pieces of the table. Oh, it did make it across that time. Ooh, that's a rough edge to get over. That's more of an edge than I thought. Could you pull the book out, please? I guess. I think we'll have better luck now, because the other table didn't really have a book underneath it. Okay. Now, I want you to observe. Okay, watch it again, and I want to know what you see. Okay? Philip, I'm going to ask you.
It kind of slows down when it hits the edge a little bit.
It slows down when it hits the edge a little bit. What do you see that makes you say that?
I don't know. I hear that it makes a noise. So,
You hear that it makes a noise.
yeah.
So it's not making a noise when it floats on one table. You can listen very closely. If you put a microphone next to it, all you would hear is the hissing of the gas. Okay? However, it does make a noise when it crosses right here, doesn't it? Did everyone hear it?
Yes.
Okay. Now, you said that. What else did you say? What happens here, Philip?
It slows down.
It slows down. What evidence do you have that it slows down?
I can see it.
You can see it. Okay. What do you see that makes you say it's slowing down?
I can see it slow down.
Okay. You can see it slow down. And this is totally okay. And I'm putting him on a spot here a little bit. Derek, tell me, what do you see that makes you think anything at all? You may agree or disagree with Philip.
I do agree with Philip, but I also see a change in direction. It's those.
You do or don't see a change in
I
direction?
do see a change in direction.
You see it change direction a little bit when it hits the junction of the two tables.
Yes.
Okay? I'm going to call it a junction. We can call it an interaction. Okay, because it actually, does everyone agree for a moment it bumps right here? You can actually hear the bump, right? You can hear that where it's going over the spot where the tables are not perfectly smooth together, okay? What else do you observe? Deja?
I was gonna say the direction.
The direction changes also? Okay. And how do you know the direction changes? What do you see that says, ah, the direction's changing?
The eyes move in a different direction.
The ice moves in a different direction. That's pretty straightforward. I agree. Okay. Amy?
It kind of rotates a little bit.
It rotates a little bit. Okay, so I'm pushing it along. And I agree, it rotated just a little bit as it hit, didn't it? Okay. And that's probably telling me something about how different parts of these two tables are hitting different parts of the bottom, right? Maybe it grabs onto one part and then the other part a moment later, and that causes it to turn a little bit. Okay, because it definitely has some turning that goes on. In fact, it wasn't turning, I think, when I first pushed it, it was coming at it, and after it hit the junction of the two tables and had that interaction, then it was turning. Okay?
It looks like more smoke comes out when it hits the crease.
Okay, good, very good observation. Looks like more smoke or more gas is coming out when it hits the crease. Why is the gas a smoky color, really quickly? Anyone?
Because it's CO2.
Yeah.
It's cold.
It's cold. It's not because it's CO2. This is no different than why on a cold day you walk outside and you breathe out and you see a cloud.
The oxygen is hitting the ice and making condensation.
Oxygen's hitting the ice and making condensation. Close. Close. Some of that's right, Amy.
Could it be because the ice is cold and inside it's hot? Also?
Inside it's hot also. No, what we're seeing is not steam from heat. It's not steam from heat. In fact, what you're seeing is not the actual gas of the air. What we're seeing is that in the air that we're breathing today, there's moisture, there's humidity, there's a little bit of H2O, water, in the air. And that water is freezing when it comes in contact with the gas coming off the block. Because the gas coming off the block is maybe 30, 50, 60 degrees below zero. And it's cold enough that it causes the little water molecules in the air to freeze from a vapor into a solid. And it is called condensation. Or sorry, it is called, it's very similar to condensation, yes. All right, so we have an interaction right here. And we said two things happen. One, it's three things I heard actually. The first one was it seems to slow down. The second one is it seems to change direction. The third one is that the dry ice seems to rotate. Okay, do we agree?
Yep.
Okay. So what we're trying to simulate here is that when I push this block with my hand, there's an interaction. My hand pushes the block. And then when I let go of the block, there's no pushing or pulling on it. It's in some kind of balanced state until it reaches right here. Okay? And when things are in a balanced state, how do they move? Constant,
Rate of change.
constant, we're using words, rate of change. I don't know. It's going at a constant pace, okay, a constant speed, and we could get out a motion sensor and prove that. Okay, we might do that in a minute if we have time today. And so it's moving at a constant rate, and then all of a sudden it hits something and it has an interaction. And that interaction can have a couple of different effects on it. That one just went across really smooth, didn't it? It can have the effect of changing direction, which I believe rotation's kind of covered under that a little bit. It can also have the idea of causing a change in the speed. Okay? What I'm going to do for a minute is put this away. Okay, and we are going to talk about the rubber bands in your hand, and then we're going to come back to this.
I lost my rubber band, bro. You have it on, stupid.
Okay, everyone pick up your rubber band. Everyone pick up your rubber band.
Mr. Brown, do I keep recording?
Yeah.
Okay.
And take your rubber band and just kind of stretch it a little bit. And what I specifically want you to do, don't overstretch it please. What I want you to specifically do is stretch it a little bit, maybe say 1 centimeter or 1 inch, and then go another. And then another. When you stretch it like that, how does it feel? Okay, so if you take the rubber band, you stretch it 1 inch, then another inch, then another inch. Elnett, how does that feel?
Height.
Is your name Elnett?
Oh, my bad.
It is Elnett, right?
Yeah.
Okay.
It feels like it's slipping away from your fingers.
It feels like it's slipping away from your fingers. Okay, good. Why? Okay. So, Tyler, how does it feel to you as you stretch that rubber band 1 inch, then 2 inches, then 3 inches?
Feels like it's trying to pull you back.
It's trying to pull you back. Okay? And does that feeling change as you pull farther apart?
Yes.
How does it change?
The rubber band gets tighter and it pulls more.
The rubber band gets tighter and it pulls more. Okay? Cameron?
I would say it's getting tighter because the fibers of the rubber band are trying to extract.
Okay, the fibers of the rubber band are trying to extract. Okay? Maybe you mean contract?
Yeah.
Like pull together?
Yeah.
Okay?
You know
Yeah.
that.
Extract usually is the idea of taking something out. Okay? Regis, how does it feel to you?
The tension gets greater the further you pull.
What do you mean by the word tension?
How? I don't know. I feel like it's about to break.
You feel like it's about to break. You're pulling yours pretty far. That's all right. So if you kind of pull it an inch and then let it go, and then pull it an inch, let it go, does it feel like the rubber band resists about the same every time? And you go an inch, let it go, an inch, let it go. So if you stretch it to the same point, do you feel about the same pull or a different kind of pull?
Same. It looked the same.
I'm hearing a lot of sames. I also heard 1 or 2 no's maybe. Edgar, do you disagree? If you pull it to about the same distance every time, do you feel the same pull back from the rubber band every time? Or does it feel a little weaker or stronger?
To me, it feels a little weaker.
A little bit weaker. Okay? Rubber bands are not perfect in this way. We're talking about something that's elastic, right? The word elastic means you can stretch it and it goes back. Lots of things are elastic. Okay? Often we talk about the elasticity of your muscles when you're just stretching, trying to get more flexibility, right? And so you stretch it and it comes back. Rubber bands aren't perfect. And there's no doubt that if you overstretch them, especially if you go a little bit too far, they begin to weaken all over the place. They can't contract in the same way any longer. Okay? So the reason that I'm doing this is we're going to use a rubber band to cause an interaction with the dry ice block. Okay? And when we do that, I'm going to try and keep the rubber band at about the same level of stretch, so that I apply about a consistent interaction the whole time to the block. Okay? And we're going to refer back to this for the next 2 or 3 weeks. So the things we're doing today, I want to refer back to. I'm not going to bring in dry ice every time I want to mention a frictionless surface. But I'm going to be approximating or referring back to the dry ice traveling on one of these tables. And I'm going to say that's what we're going to use as our model for something where there is no, I'm going to just say resistance. There's no resistance. It just kind of floats along. All right? And if this table was 100 miles long and flat, it might go for 100 miles. Okay? Can I please have the screwdriver and the screw on that table over there? I'm going to add a screw to my dry ice block. Hopefully not shatter the block. We will see.
I already did.
Well, I have to confess, I have not actually done this before. Put a screw into my block of dry ice, and so as a result, I'm not certain if I'd be better served by pre-drilling a hole or not. That's kind of a fun sound. It's not in there yet. Still very, very loose. That's pretty good. All right, let's see if that worked well for us. It'll probably make a little noise again at first, because I'm guessing the bottom surface is not perfectly smooth. Okay, and I'm looking for just a little bit more of an interaction between these two. Could you get that book out again, please, Regis? That one, and just put just the cover, no pages. Open it up so just one of the covers isn't going over these legs. I want to cause just a little bit more of a bump between these two. Okay. I want to make it a little more extreme. That's a little better. That's a little better. All right. So what I'm going to do now is take my rubber band, which I had right here. Okay. And with my rubber band, I'm going to pull, I'm going to try and keep a constant amount of stretch on my rubber band. Okay. So I'm going to stretch it, and when I stretch it, what happens to my dry ice block?
Follows.
It follows, it slides,
It gets pulled.
it gets pulled. Okay. And I'm going to ask you two to kind of scoot over here a little more, because I want you to be able to see from this side what we're all seeing. And if you can do that without walking in front of Coleman, I appreciate it. So now I'm going to pull it across the barrier between the two tables, and I'm going to try and keep a very consistent level of stretch. And I may be a little challenge for me. I'm going to have to take a few practice tries, okay? But that's what my goal is. We're going to look at it and see what we can learn from this, because we have about 8 minutes remaining. Okay, let's do it again. Now I'm trying to keep a very consistent level of stretch. What do you see happening as I keep a very consistent level of stretch?
It stretches a little more. It stretches a little more and hits the rest of the table.
Okay, there's a lot of people talking at once. Let's slow it down a little bit. What do you see happen as I stretch this and I walk? Samuel, I'm going to ask you to watch and then tell me. Is your name Samuel? Samuel, go ahead.
It goes probably about the constant speed that you're moving.
It goes the constant speed that I'm moving. Okay, so if you look at my speed, how do you know that my speed is constant? What's telling you that my speed is constant?
Maybe the length of the rubber band.
Okay. All right. Everyone agree that I'm moving with a constant speed?
No, you're not.
No? Edgar, you're shaking your head. What makes you think I'm not moving at a constant speed, Edgar?
Like, at first you start walking and I don't know where you start, like, I guess power walking, and you move across the...
Okay. So I start walking and I kind of move a little faster and a little faster, don't I?
Yes.
Do you agree, Samuel? Okay. And this kind of moves with me, doesn't it?
Yes.
Why do I have to keep going faster and faster to keep the same stretch? What's going on with that? Because I don't have a lot of time left and I want to get
The
to
stretch is lessening because it's catching.
Yeah.
Because
the stretch is lessening because it's catching.
It's adjusting.
It's catching up with me. Okay? So if I give it a little bit of stretch, I'm going to run with this a little bit, Will. If I give this a little bit of stretch, then it kind of catches up with me and then it goes at constant speed, doesn't it?
right.
And you can kind of see that. And then it gets stuck on the table interaction, which is exactly what I wanted, actually. Okay, so what do I have to do to keep the screw stretched? The rubber band stretched.
Keep going faster.
I have to keep on speeding up, don't I? To keep it, the rubber band, at a stretch of about 1 inch. Okay? And what happens when it hits that barrier in the middle?
Slows down.
Boy, it does slow down. In fact, you can see lots of little pieces of ice just flying off because it's just blowing apart the block, and there's lots of ice here. All right, so what we've seen is that as I pull with this rubber band, in order to try and keep that 1 inch, I have to go faster and faster and faster. Okay? So my interaction, and we're going to use the word here of force. My interaction, my force with the rubber band that I applied to this, it was a pull of some sort. I was trying to keep the pull constant and convince you that I was keeping the pull constant by keeping the rubber band at the same level of stretch. And in order to do that, I had to go faster and faster and faster. Okay? All right, can you please go ahead and pause the tape? I'm going to ask some of you to come up here now.